Resistive forces. So in this chapter we're introducing two different types of resistive forces. One that follows just the velocity, and one that follows the velocity squared, or rather the speed squared. Both oppose motion, so as you try and push an object through a medium, it will resist it. These are both basically a kind of drag force. The first one is typically what you would see in something that would have a higher density medium and a smaller object, typically smaller and slower. Be small, slow, and dense medium. And the v squared form would tend to be faster motion, larger objects, and less dense medium. This first one would be appropriate for something like a skydiver, a car, or an airplane. The second one would be more appropriate for something like a small bead dropped in water, H2O. Okay. They each have their uses, they each have things that we can say about them, and both of them depend on the cross-sectional area of the object. I'm actually going to make this into more of a list. Hold on a moment. Cross-sectional area of the object, the density of the medium, and the shape of the object. Now, it's explicitly written out in the second case. D is the shape factor. Rho, the funny-looking P, which is Greek letter rho, is the density, and A would be the cross-sectional area. So, yeah, we're very interested in these. They are going to cause all kinds of interesting effects. One of the first things we need to think about is what would terminal speed be with each one of them. And we'll see how long this runs. I may split the video in two pieces, but for the moment, we're going to talk about the first form, where F is equal to minus b times the velocity. In this case, it's explicit that the direction is opposite the velocity. So whatever direction you're moving, you'll experience the resistive force in the opposite direction. And we can talk about, simplest idea, terminal speed, or if you prefer, terminal velocity. Alright, what is the idea behind terminal velocity? Or terminal speed? Is the maximum speed the object would have in free fall. So for instance, if you took a bead and you dropped it in water and you just let it freely fall through the medium, the only forces that are going to be acting on it at any point will be the resistive force and gravitation. And what this means is terminal speed happens when the resistive force is equal to the gravitational one. Okay, so we're going to use that first form. Here's a little mass. We'll let it drop. As it drops, its speed picks up. As its speed picks up, our resistive force, looking like minus BV, will get larger and larger. And gravitation will be acting constantly in the other direction. We're going to take the positive direction downward here. That means we'll have a downward acceleration, at least for a while, and we'll find mg minus bv is equal to ma. And this is a generally useful equation. We'll be coming back to it. But in this case, of terminal speed, the acceleration will go to 0. So that means we'll find mg minus bv equals 0, which means mg equals bv, and v terminal, rearranging this, would be mg over b. So there we go. There's our terminal speed for this case. Okay, once you hit that speed, the force acting downward on you due to gravity will be exactly counterbalanced by the force acting on you due to the medium that you're squeezing your way through, and you'll stop accelerating. You won't go any faster at that point. Now, in this specific case, we can actually do a kind of differential equation, a little bit like we did when we were saying a is equal to dv dt and separating and integrating. And we can actually figure out, as a function of time, how the motion of this object would change. So to do that, we're going to come back to that first formula. mg minus bv equals ma, and we are going to find v as a function of t. Now, I'm going to do the simplified case here. We could have the vi that could be either up or downward. And we could start from that at t equals 0 and figure out what happens. But in this case, I'm just going to take vi is equal to 0 for simplicity. I don't need you to learn how to understand the hard version, and the easy version has exactly what we want to see. It's kind of cool. So mg minus bv equals m dv dt, because dv dt is equal to the acceleration. So now we can divide through by m on both sides. And we get a simple equation, sort of. What we're going to want to do with this is separate it so v's are all collected on one side and the dt goes to the other. So to do that, it's kind of like cross-canceling. And we'll multiply dt on both sides. We'll divide by g minus b over m times v on both sides. And we'll get dt is equal to g minus b over m v to the minus 1, which is the same thing as writing 1 over all of that. Okay. So now we'll integrate both sides. So on the first side, we'll integrate from 0 to an arbitrary final time. On the second side with the velocity, we'll integrate from our vi, which is 0, to our final v at arbitrary t, which will find us v as a function of t. Okay, this is not a terrible integral. You just need to use u substitution, where u is g minus b over m times v. That means du will look like the g will go away, minus b over m dv, and dv would look like minus m over b du. And that we will substitute in. All right, this first side, we can just straight up integrate it. We get t. The second one, it becomes an integral u to the minus 1. I'll keep it like that. And then we'll substitute n minus m over b du. Okay, I'm going to move the minus b over m to the other side immediately before I do my integration. But before I do my integration, if I plug in 0 for v, I get my lower limit is g for u. And then if I plug in v, I get, well, g minus b over mv. Okay, so carrying on a bit, minus b over m and t. Yep, that's fine. And then over here, I've already moved this stuff off. we just have integral of u to the minus 1 du from g to g minus b over mv. I'm going to write it as bv over m. It's just easier. All right, next step. We get natural log of u evaluated in our limits. And I'm going to take advantage of a rule here. Natural log of a minus natural log of b is just equal to natural log of a over b. So here I'd be getting the natural log of g minus bv over m minus the natural log of g. I'm going to rewrite it immediately as a ratio. So this will be natural log of g minus bv over m all over g. We want v, so we're going to rearrange and get v on its own. This is going to take several steps. First step, take e to the power on both sides, because e to the power of natural log means that e to the power and the natural log cancel each other out. So now we have g minus bv over m all over g. Multiply the g across. I apologize that this just takes a long time to do. Next step, subtract g. Then we'll factor the g out. And we're there. All we need to do is multiply by minus m over b. So minus mg over b, e to the minus b over mt minus 1 is our v, and finally our result. V as a function of time will be minus mg over b, plus mg over b, 1 minus e to the minus b over mt. So let's think about this. This first part, I'll mark in yellow. This is just v terminal. If we start at t equals 0, we get 0 over here. That means we have e to the 0 power, which is 1. 1 minus 1 is 0. So we start out at rest, as we should. We said that we'd start at vi equals 0. And we should proceed until t goes to infinity. When t goes to infinity, we get e to the minus infinity. That basically becomes 0. So now we have vt. So if we plot the motion, v as a function of t, it will start at 0, and it will increase asymptotically up to some limit, where eventually we hit vt. So it's cool that we can get an exact relationship out of this. Now, do you have to know how to do this? No, but knowing that the result looks like this, that is good to know. Knowing that we increase towards vt, that is good to know. Knowing it's an asymptotic increase, that is good to know. Okay, where are we time-wise? Yep, we're going to stop here and break this into 2 pieces. So in the next video, I will be talking just about some stuff we can do with the v-squared form of resistive force.